an enviable position. So we have Andrew Williams from Curtin University, and he's here to speak about astronomy in Python, which, as we were just talking about, is it's definitely a thing. A lot of astronomers use Python, but we haven't actually had all that many talks on it. So, all right, so welcome, Andrew.
Hello, everyone. Is the mic working? Yes. Well, I started in Python a long time ago. I started out as a research astronomer. I was a member of a big research group hunting for exoplanets. I was the guy in the group that wrote all the code, not one of the guys writing all the papers. So I kind of drifted out of research and ended up in a niche where I'm a better programmer than most astronomers, and I'm a better astronomer than most programmers. But neither of those are very high bars, so it's worked okay so far. That's the telescope that I've been working on. For the last few years, I've been at Curtin working in radio astronomy. I started out on real telescopes you can actually look through. Radio telescopes are kind of weird. Oh, my mouse has shut itself. I have to use a keyboard. This is the cover slide with all the logos. The logos are very important. People gave lots of money for those logos. It's a big international collaboration. This telescope started about 2000-ish. We had hardware on the ground from about 2005-ish. I got involved in about 2007. More universities have gotten involved since. It's quite a big project, and it's not the square kilometer array. The square kilometer array you probably heard of. We are a precursor, but it's an independent telescope that's been running full-time and taking data since 2012. It's a long way away. It works in the same frequencies that TV and radio stations use. So we're sitting about 8 to 10 hours drive from Perth. It's on the marker where the SKA is, but we're not actually it. So it's about an 8 to 10 hour drive from Perth. We actually fly to Geraldton and then drive out from there. And because it's in a remote place, there are difficulties. It's not much fun to live out there. The frogs aren't the problem. They go away when you flush. They come back when you're sitting down. It's the snakes that come to get the frogs that are more of a worry. That site has ASCAP. ASCAP is the CSIRO dish-based telescope. Now, a dish is most people's idea of a radio telescope. But a dish doesn't actually take a picture of the sky. You point it at the sky. If you want to take a picture, you need to scan it backwards and forwards in a raster pattern and measure the intensity at each place as you scan the dish. That instrument there, called a PAF, a phased array feed, is actually an exception to that rule. Each of those little light green and dark green squares is a separate receiving element. So that actually forms 70-odd pixels on the sky at the same time and 70 slightly different positions on the sky. But it's by combining radio telescopes together that you actually get images. These are the signs that belong to all the logos. That's sitting out there on site. You can see where everything is and how far away it is, from MIT through to Curtin. And here's a tile close up. Each one of these is a low-frequency equivalent of one of those dishes. So we have metal spiders in the desert. Each one of those is kind of like the TV antenna on your roof. It picks up a signal from the sky. And we have a box called a beamformer that does the magic of being able to point it in different directions. Each of those antennas is connected to this beamformer by a cable that is exactly 7 meters long, give or take a millimeter or so. And it's that exact 7 meter length for all of those cables that lets us do the magic of pointing it. Now, we have lots of these tiles. Some of them are clustered together in nice regularly spaced groups, and some of them are scattered at random. And which you choose is a mathematical marvel that I don't really understand. I don't know why they needed these regularly spaced ones. Most radio telescopes use what's called a pseudo-random scatter, because you want a combination of different baselines, different lengths and orientations of the distances between tiles. So each one of these tiles is your 5 by 5 meter square, and there's cables snaking across the desert to where the signals from those tiles are digitized and sent off to the outside world. And you've got an office here that you can work in with laptops, and you've got various storage equipment and power distribution, things like that. So each one of these tiles is composed of these elements. The antennas are actually 2 antennas for each of these spiders. One faces east-west and picks up polarizations that run sideways. The other faces north-south, and it's the other 2 elements that picks up polarizations oriented north-south. So if you look closely, there are 2 wires coming out of each of these spiders, one for the east-west dipoles and one for the north-south dipoles. Those wires run to a little antenna sitting up in here, a little amplifier. So the screw terminals here are connected to the aluminium dipole. They feed the signal in. The top side of this handles X. The underside handles Y. And as you can see, there's a lot of dirt around. We found out several years after putting these things out in the desert that the dirt is actually quite a strong acid when you mix it with water. The conformal coating wasn't rated to handle acid. It was rated to handle water. Now, the signal from the sky is radio waves. When you convert them in that amplifier, they turn into changing signals in your coax. They change it hundreds of millions of times a second. So each of these antennas are combined together, where imagine this is a signal from one dipole, and this is a signal from a different dipole. If the waves are in phase, the sum is very high. If the waves are out of phase, the sum is 0. So if you imagine a signal from space coming from straight overhead, hitting all of these antennas, the signal is going to hit each of these antennas at the same time because it comes from overhead. And the signals in the cables are going to be precisely in step. Each peak in voltage from every one of these antennas is going to align in time. And because these cables are all the same length, when you join them together, the signals coming from straight overhead are going to increase because they're in phase. The peaks will line up with the peaks. And it will be incredibly sensitive to any signal coming from straight overhead because each of these 16 antennas will reinforce all of the others. If a signal is coming in at an angle, then the peaks from these antennas will overlap with the troughs from these antennas, and it will all cancel out. You'll receive nothing from a source over here because the peaks will line up with troughs and they'll cancel each other out. So the tile as it is, if you just combine the signals together, is a really good way of looking at things straight overhead, but it sucks if you want to look at anything else. That's where the beamformer comes in. This box takes a signal from each one of these inputs. So we have the X polarizations on top and the Y polarizations on the bottom. So these are all of the north-south, all of the east-west orientation signals. And they go into this magic beamformer board where each channel can delay the signal by a different amount. So this channel here passes through this set of delay lines and then is summed at the end. This channel here passes through this set of delay lines and is summed at the end. The other polarizations go to a matching board at the bottom that does exactly the same thing. Usually you want to point both polarizations in the same direction. By changing the delay, we can change where in the phase these peaks and troughs overlap, and that changes where the telescope actually points, where this tile points. If you look at it slightly closer up, the delays are really very simple. Each of these black boxes is an analog switch. We can send the signal straight ahead, or we can send it through this little loop of wire. We can send the signal straight ahead, or through this loop of wire that is exactly twice as long. Straight ahead, or through this loop of wire that's exactly twice as long as the last one. There are 5 little loops of wire. The longest ones are on the back of the board. So by the end of it, we can either send the signal straight through and be added up, or we can send the signal through a length of wire that adds up to the light travel time across the tile, about 5 meters of distance for a radio wave. So we can delay the signal by anywhere up to a few nanoseconds. So each of these tiles, after it's... actually, what I might do is actually show you. That's probably the best way of just... So here's a tile. That's the direction we want to point the tile. The delays act to allow the signals from some antennas to be not delayed at all, other antennas to be delayed by a fair amount of light travel time. And if you look at the profile, that is effectively taking that entire tile and tilting it. It's taking that entire tile and tilting one corner down so it's underneath the ground and acting to reinforce signals coming from over here and to cancel out signals coming from anywhere else in the sky, simply by delaying the signals from some of those dipoles. And that all happens entirely in analog. So each of these tiles behaves like a single one of those dishes you can put in any direction. The signal from each tile is sensitive to an area that's about 20 degrees wide on the sky. And that 20 degrees is given by the wavelength that you're interested in, how physically far apart the peaks and troughs are, and it's determined by the size of the tile. If you had a bigger tile, you'd be sensitive to a smaller patch of sky. If you had a higher wavelength, you'd be sensitive to a smaller patch of sky. Now, in theory, you could take all of the tiles scattered out over a few kilometers on the desert and combine them the same way. You could have exactly the right length of cable before the tile gets summed, before you join the signals together, and you could have delays in those cables that allow you to form a single beam at one point in the sky that would be about 1/30th of a degree across. You could do that in theory. In practice, it would mean controlling the lengths of all of those cables, many kilometers of cables, to the nearest millimeter. And that's hard. So what you do is you digitize it. Each of those tiles is digitized, and then you can combine that in software. You can have every conceivable direction in the sky by having a whole heap of delays. Instead of adding the signals coming at the same instant from all of those tiles with the right delays, you have every possible set of delays to define every possible direction in the sky. Instead of choosing one set of delays, you make an image of the entire sky. You do that in software, it's nice and easy. In practice, you don't do that at all. You do something mathematically equivalent using Fourier transforms that I don't understand. So the digitizing happens in one of these boxes. We have 16 of these boxes in the desert. Each one of them has cables running to 8 tiles. And it is a bunch of custom electronics. So each receiver feeds the signal through a set of variable attenuators. We want to be able to control the voltage. We don't want to saturate the A to D converter. We have an A to D converter that samples at 655.36 million times per second. And I hope you all recognize that number. And we sample it into 8-bit integers. So we get about 10.5 gigabytes of data off the sky from each of these receivers. Or if you count all 16 of them, it's about 168 gigabytes of data coming out of the digitizers every single second. It's a massive fire hose of data that we can't possibly deal with. So what we do is we split it into channels. That data stream, instead of being 655.36 million samples per second, each of them representing a voltage at an instant, is fed into a polyphase filter bank. It's implemented in an FPGA. It's like a Fourier transform, only better. It splits it into 256 channels. Each of those channels is 1.28 megahertz wide and has 1.28 million samples per second and represents 1.28 megahertz worth of channel data. For example, channel 100 is for all of the frequencies between 128 megahertz and 129.28. Now those 10-bit samples are actually 5-bit real number and a 5-bit imaginary number. And there's a bit of magic to make sure that you choose the right 5 bits out of those 16-bit numbers that come out of the Fourier transform. But it's essentially just 1.28 million samples per second that defines a 1.28 megahertz frequency channel. We choose 24 of those frequency channels. We can choose them in a bunch. If we want to look at everything between 100 megahertz and 130 megahertz, then we can choose 24 of those channels that are together. Otherwise, we can scatter them across the whole bandwidth. So we're sensitive to signals between about 80 megahertz and 300 megahertz because of the design of the antenna. So we can take 24 different channels that are spread across that whole bandwidth if we want gaps. The 24 channels was chosen because that was as much data as we could pipe through the Xilinx FPGA RocketIO protocol on the fiber that comes out of this box. All of that is implemented in FPGAs. So we have a power supply on one side of the box. We have this rack unit here, which is your analog attenuators for 4 tiles. This unit here does the digitizing and puts the data onto the backplane. This unit here takes all 8 tiles with all of the frequency channels from the backplane and pipes 24 of those channels through 3 yellow fibers going out to the outside world. This is another digitizer box. This is another attenuator box. And the unit on the end is a little computer. It's a PC-104 single-board computer. It's about this big. It runs Linux, and it runs a lot of code to keep all that going. You control all of this by USB, via I2C, and via direct pin I/O from the single-board computer. So one MWA receiver has a bunch of code running on it. We use a Postgres instance on the receiver. That's because the people writing this code when the project started decided the only way they knew how to do inter-process communication was via SQL. Hint, don't ever do that. The guys also didn't know how to do multi-threading, so all of the locking is via SQL as well, and it's just horrible. All of this code was written by researchers and PhD students and postdocs, and nobody was actually paid to write any of it until I came along quite recently. And PhD students finish and leave, and postdocs finish and leave, and we had all this orphan code. So I'm responsible for the code that everybody else has abandoned. And most of it I rewrote while the door was still swinging on their way out. But some of it, like this horrible stuff, has stuck around. Mostly because the PC-104 platform is not quite x86 compliant, and we can't really install a new operating system on it because it's not x86 compliant. We can't really compile code very easily. So it's this horrible legacy set that I hope to get rid of soon when we dump all the hardware. So we've got Python code to start some of this stuff up, to stop it, to pass commands. Communicates by Pyro. All the stuff that I've written recently is using Pyro for RPC. The old code uses XML over TCP from a Java controller. Don't ask. And we've got code that uses direct digital I/O to control things like the power supplies and the air conditioner. We've got code that uses I2C to control gains and read temperatures and stuff. We've got code that uses USB for controlling the FPGAs. And we pipe some telemetry data out to one database server, and we control it via a couple of pipes from the outside. So 16 of these instances running out in the desert. The fiber from the receivers, the 3 fibers carrying 8 channels each, 24 channels from each receiver, go to some computers we have here in a correlator room, it's called. It's a machine room that is not quite your usual machine room, because it is a machine room that is sealed inside a Faraday cage, that is inside an office that is inside another Faraday cage. So the only thing going into this machine room is a small quantity of air, not a large quantity. They have oxygen sensors and CO2 sensors to make sure it's sufficient. Heat exchange chilled water. They don't pipe water in and out. They have one circulation system inside the room, another outside, and a heat exchanger, actually a pair of heat exchangers. And fiber. Oh, and mains power, obviously, very filtered mains power. So our machines are in this bank of racks. We have all of these fibers coming in with the data, and we have a 10 gigabit pipe to POSI to take the data back out again. So working in this room is kind of irritating. It's loud, as you might expect from a machine room. If the sirens go because the oxygen sensors are too low because the fans shut down, then you need to run. You need to get everything in and out through an airlock. This is a massive metal door with shielding around the outside, and you need to go through this airlock because if you open the door, you'd let all the radio interference out. Inside that correlator room, we've got fibers coming from a receiver fed into the fine PFB. That is another bank of custom FPGAs. And again, each of those 24 channels is then split into fine channels. So the 24 channels that are 1.28 megahertz wide are split into 128 fine channels, each of them 10 kilohertz wide. So that's 10,000 samples per second. Each of them is 4 bits of real and 4 bits of imaginary. Each of those 3,072 fine channels has 10,000 8-bit samples per tile, per polarization, per second. So that's about 8 gigabytes of data per second across the whole MWA. And that is sent in this horrible custom Xilinx FPGA specific protocol over custom SFPs, essentially. It's 40 gig pipes that we split into 10 gigabits. So that's the FPGA rack. The yellow fibers are the ones going in. They carry 8 fibers each from the receivers. So this set of 3 fibers will be 1 receiver's worth of channels, another receivers, and so on. Each one of these cards handles 4 receivers. There are 2 cards in this rack. There's another rack like this that handles the other 8 receivers. So the data goes in, and it comes out of these sort of multi-direct attached copper connectors here. So 4 cables coming out go to our media converters, which are high-end Cisco servers. So these high-end Cisco servers have a custom Xilinx card in here to receive the data. So that has ports that take this magic Xilinx protocol, and that's a $12,000 card in a $20,000 server. And all it does is translate from this horrible protocol, and there's a process running on here that reads as fast as it can and writes UDP packets out a 10 gig port as fast as it can to translate it to real world stuff. From there we can use switches. And these are pretty grunty machines. This is the back of a rack, and this is the front of the same rack. So you can see the FPGA sit in here. We've got 4 above, 4 Cisco's above, 4 Cisco's below. Each of them is a twin 8-core Xeon. It has about 3 1/3 terabytes of RAID array. That's a whole bunch of 10K RPM, 2.5-inch drives, 300 gigabytes each. And that can actually capture the full data set coming through the telescope. So about an hour and a half, we can capture that 7.8 gigabytes per second onto these drives. We can't send it back to any kind of archive in Perth at that rate, so we capture data for an hour and a half, and then we spend the next week trickling that data back to Perth. That's for what's called voltage capture. That's for things where you need the transient information. You need to see a pulsar flickering on and off 100 times a second. All of the rest of the imaging we do averages it out. So we average for at least half a second, sometimes up to 2 seconds before we save the data, simply to reduce bandwidth. So from there, that time series, those 3,072 channels, each 10 kilohertz wide, go to the correlator itself. This is the bit that actually does that delay and add, which is actually a series of complex multiply and accumulate instructions in the GPUs. So each of these IBM boxes has got twin GPUs. We were going to use one of them for the correlator and another one for real-time analysis, but the guys writing the real-time analysis failed. So we actually have one GPU spare, which is kind of handy. So each one of those servers processes data from all 128 tiles, but for only one of the coarse channels. Everything we do with this telescope, entirely I/O limited. We're limited by how fast we can get data into the box over the Ethernet, and we're limited by how fast we can get data over the PCI bus from the Ethernet card into the GPU and then back out again. So we don't do load sharing or VMs or anything like that. We're operating on the bare hardware. So we've got a database that defines what an observation is. You don't care about the details, but it's a bunch of tables that define what we want the telescope to do at any given time in the future. And we have a controller that looks at that database and says, well, 3 seconds from now, we want the telescope to be in this state. I need to notify all the bits of hardware that at time X, there needs to be a change of state. The bits of hardware get a notification that say, all right, at time X, I need to change state. They all have accurate clocks, and they all change state at the right time, hopefully. So observation control, the database contains the schedule, and it also contains a bunch of information about how the telescope is wired, which tile is connected to which receiver is connected to which input on the correlator. We have an observation controller, another legacy piece written in Java that talks to the receivers via XML of a TCP. That is the only thing it talks to. All of the other bits of hardware that have come along since 2008 are using a parallel version called PyController that I wrote that uses Pyro instead of XML over TCP. So all of the receivers are commanded to change state at a particular instant. When that instant arrives, they change state. They send their status back to another daemon in Python, which sort of integrates it all and writes status in the database. So we know not only what we wanted the telescope to do at a particular time, but what it actually did. The hardware control, this is what controls what actually takes the data. We also need to control the data flow. It sends a message via thrift to a single daemon running on a VM in Python, and that spreads it out via, again, thrift to 16 different daemons running on the Cisco boxes and 24 daemons running on the IBM boxes. And those daemons control the actual data analysis software. So the data analysis software that actually takes this massive data pipe are written in C and CUDA, and it's the Python code that sort of twiddles the knobs and aims the fire hose. So your Cisco boxes take this massive data pipe in. You have a many-to-many relation where a few tiles worth of data for all of the channels is distributed to each channel is correct. It's distributed to the right IBM box. Channel 0 is connected, channel 1 is directed here, channel 2 is directed here, and so on. That data pipeline then gets aggregated and dumped to the Pawsey Supercomputing Center where it's archived on tape. So the Python code glues it all together. The researchers doing the actual analysis on the output use Python as well. They use a package called CASA, which is, again, a massive quantity of low-level analysis code to do the imaging. But the actual user interface they're setting out is a Python command line. And what the MWA has actually done is let us go from this. This is what the radio sky looked like up until 2014, 2015, when the MWA data first got released. This is a patch of the southern sky. You can see a dot here, which is a bright radio galaxy. And you get the idea that there might be some other sources out there, but it's not clear what they are. This is the MWA data for that same region of sky. Each one of those dots is a galaxy. Radio telescopes don't see stars, they see galaxies. So each one of those dots is a galaxy. And it's produced that data over 3/4 of the sky, as well as much more detailed, in-depth looks at particular bits of it for different studies. This is the results of the survey. So that's what we've been doing, and it's lots and lots of fun. That's all I've got.
All right. Thank you. Are there any questions? Yep, I'll go to the easy question first.
You mentioned that using SQL is a really bad way to stream data. That was my interest. What do you use to stream your data?
To stream it, it's all UDP. After we get past the horrible Xilinx custom protocol, we use UDP. We don't have the bandwidth to use TCP because the data's gone by the time you realize the next stage doesn't have it. So we just stream UDP packets. And in practice, we don't lose any when it's running.
Mm-hmm. A few years ago, I went to a scientific Python conference, and one of the main themes there was reproducibility. So I'm just wondering whether your researchers publish their code as part of their research publication, and who actually has the ability to actually do reviews of that code for publication.
Ooh, CASA is the analysis pipeline, and that is certainly published and open source. The code that actually reduces the data on the telescope is also specific to the hardware that there's no real point in publishing it because it only runs on the set of hardware that we've actually built. If anybody was interested in it, we'd give it to them, but we haven't made it open source.
Okay. Yep.
It's just a logistics question. How do you get the hard drives back?
We don't send the hard drives back. We record 7 or 8 gigabytes worth of data, and then we pipe it over the 10 gigabit link slowly. So the hard drives stay in the racks. We haven't been shipping hard drives around for 4 or 5 years.
I've got a two-part question. Firstly, what does the CUDA code do specifically? And secondly, is it handcrafted or is it auto-generated? It
was actually written by NVIDIA. It's called the XGPU radio interferometry correlation engine. And NVIDIA wrote the actual CUDA kernel, and then a guy at Curtin turned that into an actual application. So the CUDA stuff is not something I've ever got involved with. And the guy that crafted the NVIDIA kernel has now left Curtin, so it's kind of a black box.
Okay. I don't think I've ever been so disappointed to go to lunch, but it's time. Yeah, thank you once again.
Thank you.